Hello, this is Charlene. We're going to be talking about modeling perimeter and area in this video. So what exactly is mathematical modeling? It's figuring out mathematical equations that represent something in the real world. These mathematical equations represent real life scenarios in the same way every time. So that's important. It's like in the same way every time. This means that the models or the equations are reliable. We can count on them to give us information we need and to save us time in the long run. Computer programming relies on good models, and the good models are simply good equations. Without good models, we would have to start from scratch every time we needed to figure something out. And who wants to have to start from scratch every single time we need to figure something out? Not me. I want to save as much time as I can. So learning how to create good mathematical models is to our advantage. Okay, our first example says the length of an American football field is 200 feet more than the width. Express the perimeter of the football field in terms of one of its dimensions, x. Okay, so the bottom line is they want us to find the perimeter of the football field. They also want us to find it in terms of one of the dimensions. Well, here's my football field, but I've actually drawn my own little football field here. What are the dimensions? Well, it's got width and length. So I can call these two short sides width, and I can call the two long sides the length. Okay, so it wants them in terms of one of those dimensions. So that means that we're going to find an expression for the length that's in terms of the width. So we're going to look at this first sentence of our word problem, and it's going to give us everything that we need in order to find that expression. So it says that our length of the football field is. So what does length is mean? Well, we can say L is means equals. The length equals, and then it says 200 feet more than the width. So 200 feet more means plus 200, and it's going to be 200 more than the width. So that means we're going to take the width and we're going to add plus 200. So that means that we now have an expression for our length. So that means that I can change the L to W plus 200. W plus 200, W plus 200, and W plus 200. So that means that now we do have the dimensions of our football field. Here's my football field. And I've got width and width and width plus 200 and width plus 200. So we're only using one dimension. We're just using W. Like I said, they said to use X, but we'll add that later. I like using width instead of X because width and length are my real life dimensions. Okay, so it wants us to find the perimeter. So what is the perimeter? Well, let's see. The perimeter, practically speaking, is adding up all the sides. So that means I'm going to add W plus W plus W plus 200 plus W plus 200. And if I add up all the sides, that will be my perimeter. So that means that I'm going to have W plus W plus W plus 200 plus W plus 200. How many W's do I have? Well, I have 1, 2, 3, 4. And 200 plus 200 is 400. So there is my answer. Express the perimeter in terms of one dimension. So there is the perimeter in terms of just one dimension. It is in terms of the width. And now we'll go ahead and do what they ask and use W. So we'll just change it up for them to make them happy. And we can put it perimeter is equal to 4x plus 400. So hopefully that helps you kind of understand how to use your word problem, the English sentences to come up with a math sentence here, which gives us the expression for the length so that we can express our perimeter in terms of one dimension. Okay, our next problem says we have a rectangular parking lot with a length that is 3 yards greater than the width. And it says express the area of the parking lot A as a function of one of its dimensions x. Okay, so the bottom line is it wants us to express the area. It wants us to find the area of the parking lot, and it wants us to find that area as a function of one of its dimensions. So again, we will need to put everything in terms of one dimension. We typically will go with the smaller dimension. The larger or longer dimension will be in terms of the smaller dimension. So our smaller dimension between length and width will typically be the width, right? So that means that I'm going to put these shorter sides, call them width, and then I'm going to find an expression for the length that is in terms of the width. Again, I'm going to look at this first sentence of my word problem. It says the length is 3 yards greater. So again, I'm going to have L and then equals, and then 3 yards greater is going to mean plus 3. So it's 3 yards greater than what? Well, it's greater than the width. So that means I can say the width plus 3 yards. So right there, I have found my expression for the length. So that means down here, I can go ahead and put W plus 3 is the expression for length in terms of width, and W plus 3 on the other side as well. Okay, so we also need to remember what we know from elementary school. What is the formula for area? Okay, so the formula for area is going to be length times width. You probably learned that in late elementary school. So how can we shorten that so it looks more mathy? Oh, how about A is equal to L times W? Okay, so now we want to fill this in. We've got a W here, and then we've got an expression for the length right here. So I can literally plug that in for that L, right? Okay, so how can we rewrite that? How about this? Here's another thing I've added. It says that that we want to write it as area as a function. Okay, so I am actually using function notation. So this is called, I can refer to this as the area function. And the area function is based on the width because the only variable, that one dimension that I'm using, is just the width. So I can rewrite that as the area function. The area function is equal to the expression for the length. There's the length, but I'm using the expression for it, which is W plus 3 times the W. So this is still the length times the width. We're just using the expression for the length. Okay. So can I simplify that? Well, yeah. Well, actually, what I'm going to do before I simplify it is just turn it around. My brain likes to use it this way and do W times everything inside the parentheses. So then I can simplify that once I've turned it around because my brain likes it better. And it turns into W times W, which is W squared, plus W times 3 is 3W. And then can I simplify it anymore? Yes, because the only thing that it wanted me to do, it actually did not want me to solve it. It just wanted me to express the area as a function. So right there, I've done that. I've expressed the area as a function. And then because they wanted me technically to use an x, I have replaced the dimension W with the x. So the x is now representing the width. So either one of these, in my opinion, are the correct answer. One is using W as the variable, and the second one is using x as the variable to represent the width. Our next problem wants us to talk about maximizing area. But I want us to talk about area and functions and dimensions first, because area has to do with real life and functions have to do with our math, and they are connected by dimensions. So let's talk about a simple area problem. When you're in elementary school, late elementary, you probably learned about drawing rectangles, and they would have a length and a width, and you would um, find the area, right? You learned that the area was equal to the length times the width. And then you learned that, okay, so we just plug in 3 times 2, and then we would multiply 3 times 2, and that would give us 6 feet, but we always were told that our dimensions were feet squared. If that was 2 feet by 3 feet, then the answer would be 6 feet squared. Okay, so let's remember that. Now let's talk about that's an area. Let's talk about the functions now, the functions. So we've got this function we learn in algebra, and it's called a quadratic function. Well, do you remember the parent function for a quadratic? The parent function? It's like the very first one before it starts transforming and getting bigger and moving away from the origin at 0, 0. So the quadratic function, the parent function is y is equal to x squared. Well, right there is a square. There's a square in area. There's a square in a quadratic function. So the thing is, though, is that the connection between the two are the fact that these are both referring to dimensions. This area has to do with the fact that there are two dimensions. There's a 2 feet width, there's a 3 foot length. That means they go in two different directions. This measurement goes north to south, up and down. This measurement goes east to west. And so that makes it two dimensions because we have two measurements, but those two measurements are going in two different directions. That's what makes the difference between a dimension and a measurement, is that the dimension also has a direction. So the quadratic function is y equals x squared. So that squared also is talking about two dimensions. So we need to understand that mathematically, a quadratic function can help us talk about areas in real life. Okay, the first problem they have given us so that we can practice maximizing areas says you have 140 yards of fencing to enclose a rectangular garden. Find the dimensions of the garden that will maximize the enclosed area. What is the maximum area to be obtained? So we have a lot going on here. Going to be multiple steps in this problem. Let's look at what they've given us. The 140 yards of fencing to enclose. Well, what is it called when we have an enclosure around a rectangular garden? It's all the sides, right? All the sides around the rectangular garden, and we could call that a perimeter. So we're going to be dealing with the perimeter here. We also are going to be dealing with the enclosed area. So we're talking about area. So we're going to be dealing with the area of this space as well. Here in part A, it tells us to define our variables. It says let x be something, let y be something, let a of x be something. Okay, so here's our picture of our garden, but it kind of helps since they've told us to think of it in terms of a or x and y, that we kind of think about it in terms of an x and y coordinate system. So let's do that. So here we've got our garden is set on an x and y coordinate system, and now it's probably a little bit clearer that the x-axis is talking about length. So we'll let the x equal the length of our garden. Okay, and then we will also look at the y-axis over here. The y-axis is talking about the width of the garden. So we'll call that the width. Let y equal the width. Okay, and then this says let a of x. Well, we always have to remember that our y is interchangeable with our function notation. So that means that, this whole y-axis is representing a function, and we can call that the area function. Well, up here, our simple definition of an area would be the length times width. So we could say length times width, or if we're calling it x and y, then that means that our a of x would be equal to x times y, right? X times y. However, if you remember from our previous discussion, quadratics. Quadratics are going to help us with areas. So I want you to remember that a quadratic, which is y is equal to x squared, is going to help us ultimately with our area. So this area function right here, as we move forward, is going to get a little bit more complicated, and it's going to end up with an x squared in it before we can actually find a maximum area. So just keep that in mind, that this is kind of a simple area function, but it is going to get a little bit more complicated so that we can maximize it, and it will look more like a quadratic function before all is said and done. Okay, the next step says write an equation for the perimeter and solve for y. So our perimeter, what is the perimeter? It's adding up all the sides. And of course, we determined that this side we're going to call y, which represents the width, and this side would also be y, and this length is represented by the x, and this would also be the x. Okay, so that means if I add up all those sides, we also have to remember what it told me in my original information, 140 yards of fencing to enclose. So the entire perimeter, the total perimeter, or what all the sides are going to add up to, is going to be the 140. So I'm going to write it like that. 140 is what the total perimeter is equal to. And then I'm going to add up all those sides. The x plus the x plus the y plus the y. And so it gives me this formula or this equation. So when I simplify that, it's going to be 140 is equal to 2x's. It's 1x plus 1x is 2x. And 1x plus, or 1y plus 1y is going to be 2y. And it tells me that I'm to solve for the y. So I am going to do minus 2x on both sides, minus 2x, and that is going to give me 140 minus 2x. And then that is going to be equal to the 2y that's left over. So 2y. And then I can divide out the 2 out of every single piece. And these are going to cancel, and that is going to give me y is equal to 140 divided by 2 is 70. And these two 2's cancel out also. So 70 minus x. So that is going to be what y is equal to. So I've got a perimeter. Equation for the perimeter is right there. It simplifies to this right here. And then I solved for the y. So that gives me an expression that I can use to replace y with in a future equation. Okay, step C says to create a function modeling the enclosed area in terms of x. So they want us to come up with a function that is an area and that it is in terms of x. So earlier we came up with this area function, a of x is equal to x times y. Well, this area function is in terms of x and it's in terms of y, but we need it to only be in terms of x. So while we were working with the perimeter, we solved for the y, and we came up with this expression that y is equal to that expression. So I can now take this expression and I can substitute it in for the y, and that is going to help us to meet our goal of having a function for the area that is only in terms of one variable, the x. So when I substitute that expression for y in, I've got the area of x, or the area function in terms of x, is equal to x times this expression for y, which is 70 minus x. And then I can simplify that by distributing the x into the parentheses to every part. So then a of x is equal to 70x minus x squared. Okay, so this gets us exactly where we want to be. So because this is an area function that includes the x squared, and that x squared is a quadratic. This is a quadratic. So this is definitely going to help us with a real world area, and it's going to help us to maximize the area. So this is the correct area function. This has the level of complexity that we need in order to maximize the area of our garden. Okay, part D says to find the vertex of the quadratic function. And the last step we did find a of x is equal to 70x minus x squared, which is a quadratic. It has an x squared term. So we know that it's a quadratic, and it is going to help us find the maximum area for our garden. Now, is it in perfect standard form? Standard form is ax squared plus bx plus c. No, it's not. So I'm going to rewrite it just because it makes my life a little easier, just to make sure that I can observe some things about it. So now that I've written it in standard form, which is the x squared term first and then the x term second, I can see that I have a -1. It's a negative coefficient in front of the x squared term. So what does that mean about the graph of this quadratic? It's going to be a parabola, but is it going to be a happy parabola, or is it going to be an unhappy upside down opening toward the bottom? It's going to be opening toward the bottom. This is what the negative x squared means. So where is the vertex of this parabola? That vertex is going to be on the very tippy top. So that's what it wants us to find. It wants us to find the coordinates of that vertex. So how are we going to go about that? Well, the first thing I'm going to do is use what I call the magic bullet. The x value of the vertex can be found with this equation, -b over 2a. Well, where is the b? Well, the b is whatever is in front of the x term. So the x term is going to be 70. So that's going to be my b. So I'm going to fill this in. It's going to be -b, so -70. And that is all going to be over 2 times a. Well, the a is whatever is in front of the x squared term. So that's going to be that -1 in front of the x squared term. So it's going to be 2 times a -1. And when I simplify that, the two negatives are going to cancel each other out. 70 divided by 2 is going to be 35. So that means that the x value of my vertex is going to be 35. So how am I going to find the y value? I'm going to find the y value by taking this x value. This is my x value, the x value of my vertex, and I'm going to plug it back into my original function, and it is going to pop out my function value. And I have to remember that my function value is the y value. My function value is the y value. So let me get rid of that. There we go. So we're going to put 35 in there. So that's going to be -35 squared plus 70 times 35. And when I put that in my handy dandy calculator, it is going to pop out a y value of 1225. So the y value is going to be 1225. So the vertex, which is at the top of my parabola, has the coordinates of 35, 12, 25. Okay, Part E says, what is the maximum enclosed area? So we are getting down to the wire. We are now starting to ask, what is the maximum enclosed area of our garden? Well, we have to think about what this vertex means. This vertex represents a point that is a maximum point on this graph, right? It's a maximum point on the graph. So we also have to understand what I said earlier about the fact that this function value is the y value. The function value is the y value. So this y-axis represents the function value. So all of these numbers along the y-axis are going to be an area. These are going to be areas, because the y value is the function value, and this is an area function. Okay, so that means that over here on the x-axis, the x represents the lengths of the sides of the rectangular shaped garden. These are the lengths. So up here we have an x value, we have a y value, which is also the function value. It will actually produce areas. Whatever that y value is going to be an area number. So that means that the length at this vertex is going to be a length of 35, and it means that the area at this point right here is going to be 1225. That is the maximum area at that maximum point at the vertex. So the maximum enclosed area, for our rectangular shaped garden area is going to be equal to 1,225 square yards. Okay, our final question says, what should the dimensions of the rectangle be to get the most area? To answer this question, we're going to go back to our original simple area function. We have determined that the total maximum area, the function a of x for our parabola, was equal to 1,225. That's the total. So we're going to plug in 1,225 to represent our function value for our quadratic function. And then we're going to plug in for the x, the 35 that we came up with as well, 35. But now we're going to find out what the other dimension that's represented by y that would give us this total of 1,225. So I'm going to solve for the y. So we're going to divide out 35 on both sides of the equal sign. And of course, they are going to cancel right there. And when I put that in my handy dandy calculator, 1,225 divided by 35 leaves me with 35. So that means that my dimensions are going to be an x times a y, or a length times a width, of 35 yards by 35 yards. And a 35 yard by 35 yard garden space will give me my 1,225 maximum area. So 35 yards by 35 yards are going to be my final dimensions to get the most area. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.